So, welcome to the second part of lecture 5 on graph theory. So, now we will learn what is minimum spanning tree of a given weighted graph. First we will learn what is weighted graph, that every edge is given some weight, that weight could be the distance between these two vertices, or it could be the cost of moving from one vertex to another vertex. And then we learn what is a spanning tree of a graph, and we will try to find, there could be several spanning trees of a graph, of a given weighted graph, and we will find the spanning tree which is having the minimum cost. So, let me just formally introduce the things. So, minimum spanning trees. Okay. So, this is with respect to weighted graph. First we will learn what is spanning tree. A spanning tree of a graph G is a subgraph that is a tree which includes all the vertices of G. So, a spanning tree of a graph is a subgraph, that is a tree which includes all the vertices of G. Let me just give an example to illustrate this thing. Consider this graph. So, this is so now this is not a simple, this is simple graph, but it is a weighted graph. So, this edge weight means every edge is having some weight. So, this edge has weight 2, that means you can interpret that weight in different manners, like the weight might represent the distance between these two vertices. It could also represent that what is the cost of moving from here to here, and many more. So, this edge has weight 2, this edge has weight 2, this edge has weight 3, this edge has weight 3 again, and this edge has weight 5. So, this is called weighted graph. Okay. Now, this graph has several spanning trees. So, this is one spanning tree. Well, so this is a spanning tree because it is a, let me call it T1. So, T1 is a spanning tree of the graph G because it is a subgraph of this graph G, it is a tree and it includes all the vertices of the graph. So, this graph has 4 vertices and this tree is also having 4 vertices, and there could be several spanning trees of T2. This is another spanning tree of the graph G. You can see that this is also a subgraph of the graph G, and it is a tree and it includes all the vertices of the graph G. That is why this is a spanning tree. Now, what is the cost of this tree? The cost of this tree, this spanning tree T 1 is just the sum of edge costs. So, this edge has cost 3 or weight 3, this edge has weight 2, this edge has weight 3. So, the cost of T 1 is 3 plus 3 plus 2, that is 8, and the cost of this tree, this spanning tree is 3 plus 2 plus 2. So, this is the cost of T 2 is equal to 7, and you can, this is a small graph. So, you can check that T 2 is the unique minimum spanning tree of G. Okay, so, that means you can't find another spanning tree of weight less than 7. So, let me formally say the definition of minimum spanning tree. This is also denoted by MST. A minimum spanning tree of G is a spanning tree of G for which the sum of edge costs is minimum. Okay, so, we understood the definition of minimum spanning tree. Just in general, let me tell this spanning word is used. So, when I say a spanning cycle or Hamiltonian cycle, it is a cycle which includes all the vertices of the graph. When I say spanning path between two vertices u and v, that means it is a path between u and v which includes all the vertices of the graph. Sometimes we also use this word spanning subgraph. Spanning subgraph is a subgraph of a graph G which includes all the vertices of the graph G. Okay. So, the other way of understanding spanning tree is that it is a spanning subgraph, which spanning subgraph means it's include all the vertices of the graph, and it's a tree. If the spanning subgraph is a tree, then it is called a spanning trees. Okay, so overall the spanning means it's span or it includes all the vertices of the graph, original graph. Now what we will do is that we will learn a technique to find minimum spanning tree in a given weighted graph, and for that we learn here Kruskal algorithm to find a minimum spanning tree in a given graph, given weighted graph. Okay. Kruskal algorithm. and I use an example to illustrate this algorithm also. So, this is the weighted graph that I will be using to illustrate Kruskal algorithm. 2, 4, these are the label for the vertices, these are not weight, this is 3, 5 and vertex 1 is here, and the cost of this edge is 35, cost of the edge 2, 4 is 10, the cost of the edge 3, 4 is 20, cost of the edge 2, 3 is 25 and cost of 1, 3 is 40, cost of 3, 5 is 15 and the cost of 4, 5 is 30. Okay. So, this is the graph, weighted graph that I will be using to illustrate the algorithm. The basic idea is to you try to get a spanning tree of this graph such that you are using the edges of lower weights. So, that is the basic idea. So, let me just write down formally the algorithm. It is very intuitively very clear that why this works. So, T is the set of tree edges, that means the edges which will be included in the spanning tree. So, initially this the set T is empty, T is phi, and then I will be using another set called Vs. Vs is the set of all vertices basically. So, that also initially empty, and then I construct Vs. So, for each V belongs to the vertex set. So, input to this algorithm is a graph or weighted graph G V E, and output of this algorithm is a minimum spanning tree. Sometimes the minimum spanning tree is not unique if there are two edges or two or more edges with the same weight in such cases. For each vertex V in the vertex set capital V, do add a singleton set V to Vs. So, Vs is a set of initially. So, what well I will illustrate parallelly here. So, Vs for this given graph is consist of these singleton sets 1, 2, 2 is corresponds to the second vertex, 3, 4, 5. Well, now what we do is that we order the edges, say V w in non-decreasing order of weights and store somewhere, store in Q. Generally this is stored in the priority queue, but this is a data structure which is which I am not assuming that you know data structure. So, you store them somewhere. So, you arrange the edges in non decreasing order of weights. That means, this is what I want to say. So, the edge which is having the lowest weight, that is 2 4, 2 4 is the edge which is having the weight 10, and this is the minimum. So, this will come first, and then the edge 3 5 has weight 15. So, 15 is less than 10 is less than or equal to 15. The next edge is 3 4 has weight 20. The next edge is 2 3. 2 3 has weight 25. Next edge is 4 5, which has weight 30, and then we have 1 2, which has weight 35, and then we have 1 3, which has weight 40. So, all the edges will be stored in this order, and then you are sort of ready with the basic setups, and then you run this while loop, while the cardinality of V s is greater than 1. So, at this moment my cardinality of V s is equal to 5, because there are 5 sets. So, it will go inside the loop. What it will do is that it will choose an edge V w of lowest cost. That means, it will first choose the edge 24, which is having the lowest cost 10, and then what it will do is that it will delete that edge from Q. So, these are the edges which are stored in Q. So, you delete V w from Q. So, after the first iteration, the edge 2 4 will be deleted from the Q. Now, what we will do here is that if V and W are in different sets W 1 and W 2. So, this W 1 W 2 corresponds to these sets here 1 2 3 4 5 are in different sets in V s. Then you do the following. What you do is that you replace W 1 and W 2 in V s by W 1 union W 2, and you update your T. If this is true, okay, I will just explain this one, T union. So, T is a set of tree edges, basically all the edges which will be considered in the spanning tree or minimum spanning tree. So, you include this edge in T, that V w is included, and that is all, and at the end you return T. So, once you are outside this loop, you return the T, which is the set of tree edges. Okay. Now, let me explain this one. So, here the edges, the first I will consider the edge 2 4, because I am inside this loop here, because my cardinality of V s is 5, which is greater than 1. So, I choose an edge V w of lowest cost, that is 2 comma 4 for me, and then I will delete 2 4 from Q, and then I will check whether 2 and 4 are in two different sets. Yes, 2 is here, this is my W 1 at this moment, and 4 is in a different set. So, this is that in two different sets W 1 and W 2. Since this is true, what I will do is that I will revise my V s, I will revise my V s. So, these two sets will be replaced by its union. So, my new V s set is now consist of 1, 2, 4, 3 and 5. I hope that this is clear, and the action here which I write is that you add this edge in T. So, add means I am updating my T. So, the T initially it was null. So, add means I include 2 4 in my tree, and I will include more edges slowly. And again you see that now the cardinality of V s is 4, which is greater than 1. So, I choose an edge which is of lower cost. So, I will choose 3 5 and I delete it from the Q. Now, I am dealing with the edge 3 5. See, I am always trying to use an edge of lower cost. First I have used 2 4 and that is included in the tree. Next I am using 3 5 and I will see whether 3 5 can also be included in the spanning tree. So, 3 5, now 3 is in one set and 5 is in a different set. So, they are in two different sets. So, this is true. So, I will add this edge in the in T, and what I have to make some update in V s. So, this is my V 1, sorry, this is my W 1 and this is my W 2 at this moment. So, now my new V will be 1 2 4 3 5. I will take their union to update my V s. So, the next edge, so the cardinality of V s is 3, which is greater than 1. So, I have to take the next edge 3 4 and I will delete it from the Q. So, 3 4 is so 3 4, 3 is here and 4 is here. So, this is my W 1 now, this is my W 2. So, they are in two different sets. So, I will add this in my tree set of tree edges. So, 3 4 edge will be added, and what I will have to do is that I have to update my V s also. So, the new V s will be 1 and union of W 1 W 2, that is 2 3 4 5. Well, still the cardinality of V s is 2. So, I can go inside this while loop. V s is still, the cardinality of V s is 2, which is greater than 1. So, I will choose an edge of lower cost 2 3, 2 3, and now I will check whether 2 and 3 are in two different sets. That is not true, they are in the same set. So, I will reject this one. I will reject this edge. In fact, you can see the other way of thinking is that 2 3 is creating a cycle with the existing edges. That is why we reject 2 3. Let me just tell in that respect also. So, till now I have 2 4 in my tree. So, 2 4 is in the okay, I will use red color. So, 2 4 is there in my tree set, and then 3 5 is in, and it is in the T, and 3 4 is also a tree edge. 3 4 is tree edge. Now, if I include 2 3 also, that will create a cycle, but I am looking for a spanning tree. So, that is why we reject 2 3. Okay. This is another way of thinking, which is same as 2 3 is in the same set. That means, if we add 2 3, there will be a cycle in the existing tree. So, that is why we reject this one. And next, still the cardinality of Vs. So, we will not update Vs also. The cardinality of Vs is still 2. So, we go for the next edge, then that is 4 5, and again I see that 4 and 5 both are in the same set, which is equivalent to say that 4 5 is creating a cycle in the existing tree. So, we will reject it. So, there is no update on Vs. The cardinality of Vs is still 2. So, we are inside the loop. Next, we consider 1 2, delete 1 2 from Q. Now, 1 and 2 are in 2 different sets. So, this is my W1, this is my W2, they are in 2 different sets. So, I will add them. I will add this edge in my set of tree edges. 1 2 will be considered, and here you can see that 1 2 is not creating any cycle, which is same as 1 and 2 are in 2 different sets. So, I will update my Vs now. My new Vs is this one, 1 2 3 4 5, and now I can see that my Vs is having only one set. So, the cardinality of Vs at this moment is equal to 1. So, I am sort of outside this, I am out of this while loop. So, I have to stop here. So, I will not check with 1 3 anymore. So, I will stop here, and I will return this tree, and as you can see that this tree, what is the weight of this tree? This tree is 1 2 is added at the end. So, this is the tree, this is the spanning tree shown by the red lines, and the cost of this tree you can compute, and you can check that this is the minimum spanning tree. You can't find any tree which is of lower cost than the tree given by the Kruskal algorithm. There are several ways of thinking the same algorithm. So, instead of thinking them that Vs is a different sets, one can also consider Vs as you start with few vertices, these isolated vertices basically. So, the singleton set here is equivalent to all the vertices are initially isolated vertices, and then you add 2 4 first, that is equivalent to you join these 2 vertices, these 2 isolated vertices, and next is 3 5, which is equivalent to you join these 2 vertices 3 and 5, 2 4, and this is 1, and then 3 4, that means you are joining these two vertices 3 and 4, and finally 1 2, that means this. This is the spanning tree basically, and there are different way of representing or thinking this Kruskal algorithm. Well, so I hope that you understood Kruskal algorithm and how to find a minimum spanning tree given a weighted graph. Thank you very much.